Buenos días, estamos aquí en la charla del capítulo de acústicos hispanohablantes de la ASA. La misión del capítulo es congregar a profesionales, estudiantes, investigadores en el área de la acústica y el sonido, principalmente en el área geográfica de América Latina. Sin embargo, el capítulo invita a miembros hispanohablantes desde cualquier parte del mundo. Como pueden ver, tenemos miembros regados por todo el mundo, principalmente Colombia, México y Argentina. En este momento son los países de los que más integrantes tenemos. Tenemos un buen número de estudiantes que son, de integrantes que son estudiantes. Y la gran mayoría de nuestros miembros están en las áreas de acústica arquitectónica, ingeniería y control de ruido. Sin embargo, para quienes nos han seguido por un tiempo, saben que hemos tenido charlas sobre acústica bioanimal y otras áreas diferentes a la arquitectónica. Hacerse miembro del capítulo es simplemente llenar un formato, no hay un costo de participación. Y también los invitamos a hacerse miembros de la Sociedad Acústica Americana. La junta directiva del capítulo actualmente es esta que tenemos acá. Hoy nos acompañan algunos de los miembros aquí en esta charla. Y nos pueden seguir por las redes. En el canal de YouTube tenemos grabaciones de todas las charlas que se han hecho en estos últimos años. Okay, now we start with the topic that brings us here today, spatial room impulse responses, measurements, analysis, and analyzation. Our presenter today requires very little introduction. I think he's made a good name of himself coming out of the University of Technology in Helsinki with studies in acoustics, audio signal processing, and computer science. He's now the head of the Department of Information and Communications Engineering at Aalto University, where he leads the virtual acoustics team to create novel, objective, and subjective ways to evaluate room acoustics, especially concert halls. Additionally, the team currently contributes to sound rendering algorithms for augmented and virtual reality applications and novel wood fiber-based absorption materials. He's a fellow of the AES, an honorary member of the Acoustical Society of Finland, and we're happy to have you here. So I'll pass it on to you, Tapio.
Thanks, Anna. And good morning there. It's late here. See the sun shining on my face. It's still late evening, but the sun is still there as I'm in so north in Europe. Okay, responses, and then the motivation behind this is basically all the work that we have done when studying concert halls. You can see here on the right the picture of one concert hall that that we have been measuring, and then also with these measurements we have been then able to oralize all these halls to do all kind of things. So let's see. Okay, what is a spatial room impulse response? So in the top figure you see a pressure signal of a room impulse response, which you are probably familiar with. So here we have the direct sound, and then we have the first reflection and a couple of other reflections. And what means spatial room impulse response is that we have also some other data, so metadata. In this case, we have actually the azimuth and elevation information where every single sample in this impulse is coming from. So it looks really noisy, but as you can see, there are some stable parts. For example, in this case, where the direct sound is, there's a stable estimate that it's coming in front of you because the azimuth is 0 and the elevation is about 0. So I mean spatial room impulse response is that in addition to pressure signal, we have also information about the spatial position of this, where the sound is coming from. And where you can use it, one main thing that we have been using is oralization. So in our case, what we did, what we have done a lot in concert halls, but also in other rooms, I will explain it in the end with other applications, is that you can capture sound of a concert hall or impulse responses of concert hall from every single loudspeaker with the microphone array, and then analyze all these spatial information, and then use this information when you are doing oralization. This is from our lab where we have at the moment 48 loudspeakers around you, and then you can listen. You can convolve that with anechoic signals, and then you can oralize whatever space you have been measuring. So in addition to just pressure information and monosignals, you have the spatial information, and you can really create the same sound field that you have in situ in some space. What else it gives? It gives you the spatial information, as I said, so we can actually also visualize the spatial energy, for example. I will explain these in detail later, but for example, these are the pictures that we are using a lot, where you have time and space. So in a frequency response, you have all kind of, in the spectrogram, you have frequencies and time, for example. But here, what you have time in different. Here you have kind of expanding cumulative energy, but how it's distributed in space. And from these, you can read where the reflections are coming from and where is the sound energy coming at a certain moment. And then based on all this work that we have done in concert halls, we have been able to understand much better the sound of the concert halls. So these are the vocabulary that we have been collecting and what we are using currently in our current research. So what kind of differences people hear from the concert halls? So basically, it's the inner circle is the main things, like loudness, which is related to intimacy to some extent, then spatial impression, reverberance, clarity, timbre, balance, and then of course some external sounds like echo, image shift, and background noise, and so on. And then all these other attributes that you have here are something that has come out in our studies and also in the literature. So this is kind of the vocabulary we can use when we are discussing about acoustics of concert halls. And this is all collected based on these spatial room impulse response measurements and oralization of these measurements. So I will motivate the technique that I will then go in detail, the spatial decomposition method. Just I will tell you how it's kind of done traditionally. Then some examples of measurements of spatial room impulse responses, and then analysis with this spatial decomposition method. And then I explain it in detail that how it works. It's actually really simple concept and a really simple idea how it works. And then some analysis results, some visualization results, and then also oralization, how it's kind of used in oralization, how you can reproduce any sound field where you can measure spatial room impulse responses and then use it, and then applications in the end. Okay, maybe the simplest thing how to do spatial oralization of spatial sound is to use dummy head. I think most of you are familiar with the dummy head. So in this case, you have a sound source here, and then you have a dummy head where you have two microphones in the ear, and then you can measure, you can actually record, or you can measure binaural room impulse response. So the sound is emitted from here, and then it hits the head here, and then you have the reflections and the reverberation field there. And then if you want to oralize that, you have the two channels, left and right ear signals, and then you have your source signal and then you convolve that, maybe do some equalization or something. You can equalize the headphone response or equalize a little bit to make it sound better. There are many techniques, but this is kind of the basic, most simple concept. It's simple and fast. It's kind of simple processing, but of course you have static orientation. So when you are listening that with headphones, if you turn your head, there is no way of changing or taking into account the head rotations. So it's static as such. So if you turn your head, the whole soundscape turns as well. It's only one specific head because it's a dummy head, so the HRTFs probably don't match to your HRTFs, and it's not good for all. And you can use headphone playback, maybe also some other techniques nowadays. But the sound quality is not perfect because it's not your head, and then the sound quality is actually degraded. The other option is to use microphone arrays. So you have multiple microphones, and based on the differences between the microphones, you can actually compute where the sound is coming from at certain time moment. And the basic idea is that you have multiple microphones, then you do some encoding and decoding. Basically, you encode it to some other format because you cannot use just the microphone signals as such. And then you do the convolution with the source signals, but you want to oralize, and then you have a bunch of options to do even headphones or number of loudspeakers. And then this encoding and decoding really depends on what kind of microphone you have and then what kind of loudspeaker array you have. So we have many different microphone arrays. What we have is that this is the first order microphone, which many of you are really familiar with, as well as the Eigen mic, where you have 32 capsules. Nowadays, we can also buy one where we have 64 capsules. And these are omni capsules on a rigid sphere. So of course the sound is shadowed. If it's coming on one direction, it's captured differently because of the scattering from this ball. Or you can have an open array. So these are the closed arrays where you have a kind of the rigid sphere there, which modifies the sound field, that you can use this information when you are encoding and decoding it. Or you can have omni capsules. So this is one that we are actually using. There is 6 omni microphones, or you can have 6 omni microphones around and then one pressure microphone here. So there are multiple options how to do different things. The minimum number of microphones is 4, so that they are in the tetraedric form. Basically, how you have them in the first order ambisonics microphone, but then the way of processing is different. So the most familiar is probably ambisonics, which is based on spherical harmonics decomposition. So basically how it works is that you have this kind of microphone, for example, this one where you go higher order, or this is the first order one. And then you have your microphone array responses. Then you encode the signal to spherical harmonics domain. So it's one transformation. You can think, if you are not familiar with, you can think it as a Fourier transform is from time domain to the frequency domain. And then the spherical harmonics is basically transformation from time domain to kind of spatial time domain. And then you do the convolution there, and then you have ambisonic signals, which you can actually rotate quite easily. And then you decode it based on what is your reproduction system. If it's headphones, then there's a different decoder. If it's loudspeakers, then it's a different decoder. And then this actually works quite well. There are some problems depending on the order of the spherical harmonics and depending on which kind of reproduction room, how many loudspeakers you have, and so on. But it's really used method, and it's actually quite nice. It's also what we call a linear method, because these are all linear transformations that you have there. But then if you are listening with loudspeakers, there might be some sound quality problems, and it's not accurate in space and frequency domains, which is coming just for the physical facts that it cannot analyze exactly the directions, and then also kind of the frequency domain problems are really related to, for example, this one, that the microphones are on top of this kind of rigid sphere and not really close to each other, which means that at high frequencies there is no way of kind of having really flat frequency response, because you have to use all these microphones in the analysis. But one great thing is that you can do recordings, and that's why it's actually quite a lot used, because you can do recordings. When I'm talking about spatial room impulse responses, I'm talking about measuring impulse responses. So you cannot, it's not recording, it's an impulse response measurements, and then you do the convolution afterwards with the source signals. Then we have a bunch of parametric methods. And the idea in the parametric methods is that we capture the sound with microphone array, and then we somehow analyze that so that we extract, for example, what I showed, kind of pressure signals, and the pressure signal, and then metadata, which is telling you where the sound is coming from. Or you can use some auditory models, for example, to do the analysis to some kind of, let's say, spatial hearing related parameters. So you need a microphone array or spherical microphone array. There are many different analysis methods. Directional information becomes available also for visualization and oralization, and there is a lot of different rendering methods to use. But then the problem is, or not the problem, but it's kind of one of the problem is that there are many methods, and then you have to really know what are the features of all these methods, because all these methods, different methods, they have different problems. They have different pros and cons. And then you really have to understand what is kind of the benefit of one method, and then apply the suitable method for your problem. And yeah, as I said, in these parametric methods, which these are some of these, the idea is that you do the kind of directional analysis, and then you have kind of you have the omnidirectional room impulse response in optimal case, and then you have some direction of arrivals of direct sound and reflections, maybe estimate of the diffuseness or something, and you use this information in the rendering, and then you do the convolution and you go to different reproductions. So this is table. This is really busy table, but I'm not going into details. Just saying some words about this. This is the spatial impulse response rendering, which is quite nice method, and it's really used the first order ambisonics microphone, or just 4 capsules, first order ambisonics microphone, and then you can actually do quite a lot with that. And it works for spatial impulse responses. Then there is also higher order spatial impulse response rendering, where you can have higher order microphones. Then what I'm now telling you today is this SDM, which my team has developed, where you use this kind of open microphone array. and it's based on actually the time differences between microphone capsules. So that's why you need an open array, because the sound is coming from one direction and then it hits all these microphones at different time, and you are using this time information to analyze where it is coming from. And then there are different actually combinations of these different combinations and a little bit different techniques, but I don't go in the details of these. Okay, let's go to this spatial decomposition method. So as I said, it's a parametric method, and then we always need a sound field model. So in this case, the sound field model is that we have one direction in one short time window. So it uses very simple model. So we have one direction for one pressure value per time. So for example, here we have the direct sound, then we have one reflection, then we have some scattered sound. This is a reflection, maybe a bunch of reflections. And then we assume that all for these events, we can also analyze where they are coming from. So in a way, you can think also that every single sample in your impulse response is kind of an image source. So for example, here we have, this is just the loudspeaker array that we are reproducing. But if you are sitting here, you can think that, okay, the direct sound is coming from here, this big spot. So the size of the spot is actually the amplitude. And then all these reflections, they are basically image sources around you, wherever you are. This is helpful for somebody who are used to or who are familiar with room acoustic modeling. And how it works, this is actually basically everything that is needed. So it's based on time difference of arrivals, TDOA, estimation directly from the microphone signals. So when we measure an impulse response, we are actually emitting an impulse. Typically, of course, we use sweeps to do it, but then the sweeps you can convert mathematically to impulses. And in this case, we have 4 microphones here, and then because we have 4 microphones, we have 6 pairs. Their pairs are like this and this, this and this, this and this, and then this and this, and this and this, and this and this. So you have 6 pairs, and you analyze with cross correlation, you analyze the time difference of arrivals where the sound is coming from. So if the sound is coming from, for example, lower here, from down to up here, it hit first this microphone, then it hit this microphone, then it hits this microphone, and then this one. And then you have different time differences between all these pairs. And how you do the analysis mathematically is that this is a cross correlation. So you compute the cross correlation, and then you find out the maximum of the cross correlation. So in this visualization, you see that the microphone bit 3 and 4, this is the cross correlation, and then this is the maximum. So this is your time shift, how many samples there are in between those. And then it depends, if it's negative, it depends on the order of the microphones, is it negative or positive. Then of course, because the microphones are really close to each other, these might be, we need subsample accuracy. So it's not enough to have, like, let's say that this is 4 samples and this is 6 samples. So we can actually estimate with this formula. I don't go into details on that, but basically all these time delays are this tau, which is a round number of samples, plus this, which is plus minus 1, some fractional delay. And then this vector of all these 6 time differences are the time differences which are kind of you have also kind of subsample accuracy. And then this V is actually just the geometry of the microphone. So it defines that how far they are from each other. And then to find out the estimate this k, which tells you the direction, it's actually the pseudo inverse of this matrix, and then multiplied by this time vector. And then you have it. I have an example which is explaining you it kind of you see it in practice. So this is from real measurement. This is the Concertgebouw in Amsterdam. From our measurements, we had a bunch of loudspeakers there, but now I'm using this one loudspeaker there in the middle, and this is the receiver point, which is in 21 meters from this line, from this, and then we are using these 6 microphones, and then this is the loudspeaker that was there. So when we measure 6 impulse responses, you have 6 microphones, you get 6 impulse responses. And I have isolated now only the direct sound so that you understand the basic concept. So this is only the direct sound. You can see that as the microphone array is like this, the sound is coming from right to left. So it hits first the microphone number 1, which is the blue one. Then you have all these 4 microphones which are almost at the same time, and then the green one is the latest one, which is the back microphone there. Now if you do the cross-correlation analysis, you have 15 pairs. You have 6 microphones, so you have 15 pairs. And this is the result of this cross-correlation analysis. So you have one delay which is quite a lot. Then you have many which are on top of each other, because of course all these 4 microphones there, because the sound is coming from this direction or almost this direction, they are almost at the same time. And that's where I said that you really need subsample accuracy, but luckily there are closed form solutions for this, and then which is one equation you can actually find it out. But you have now these 15 different estimations of time differences between microphone capsules. And then how you compute it is that this, as I said, this V is actually coming from the geometry of the microphone. So this we can compute from the geometry of the microphone, and these are all the delays. So the delay, the longest delays is between this first and last microphone. Then we have the 4 delays between the first and these 4 microphones, which are almost in the parallel plane. And then negative one is kind of all this one and all these. And then we have something which is really small. And then this is multiplied by speed of sound and then the sampling frequency. And then if you compute this out, you get the Cartesian coordinates, and then you actually have if you then go to the spherical domain or spherical coordinates, you get that it's minus 4 degrees azimuth and 4 degrees elevation. And in this case, it was really coming from the air, so the minus it's a little bit on the right side and 4 degrees elevated because there's the stage which is actually quite high there, so it sounds really reasonable, so that it was 4 degrees. So this is how it works. And then when we want to analyze the whole room impulse response, is that what we do is that we take like 1 millisecond window, and then we analyze this as I showed, first the direct sound, and then we move this window one by one sample by one sample, and then you analyze all the time where the sound is coming from with this short window, and then for every single sample, because your step size is 1 sample, you actually get the estimation that the azimuth and elevation estimation. Here's another example to kind of make the concept more understandable. This is our variable acoustic room in Aalto, in our lab. We have these kind of panels which you can open or close. So when they are open, the sound can go in there, and then there's 10 centimeters of mineral wool. And when it's closed, then the sound is reflecting there. So here's one measurement where I have 1 loudspeaker here. There's 3, but of course, in this case, I'm only plotting this 1 loudspeaker. the impulse response from this one loudspeaker, and I had this open microphone array there. And now I'm using one pressure signal out of this one microphone, and and based on this cross correlation analysis, I get the azimuth and elevation for all of these. And then yeah, here now in this case I have open panels behind the loudspeaker, and then I have open panels behind the microphone in the next measurement, and you can see that they change a little bit. If we zoom in the first part, so this is now kind of the zoom in the first reflections here. You can see, for example, that okay, this is the direct sound, then we have the flow reflection, then probably ceiling, and this is probably the reflection which is coming from behind the microphone. So the sound is going from loudspeaker to the wall and then back to the microphone array. And you have the peak, and why I know that it's coming from the back is that because the azimuth angle is about 180 degrees estimated, and elevation is about 0, as you can see here, then I know that it's coming behind the microphone array. Because the direct sound is coming in front, it's 0 degrees. This one is actually 0 degrees, but it's minus 40 degrees or minus 30 degrees in elevation, so it's the flow reflection. This reflection is this is actually from the side, because we see here, you cannot see really, but you can see that it's coming from the side. But okay, the main point is that if I change this absorption to the other side, so I don't touch the loudspeaker, I don't touch the microphone, I just close the doors and open the doors, and then what happens is that it's exactly the same. The direct sound and the first reflections are exactly the same because I don't touch those walls at all. But then this back wall, when it's now attenuating sound, the reflection disappears. And then of course the estimation goes crazy, and it's really varying a lot because there is not really sound energy. And that's why the sound energy is going to all directions, and that's why it's fluctuating a lot. But you can see that, okay, there is a clear reflection when it's reflecting, and when you put the absorption there, it disappears. So even though this looks really noisy, this azimuth and elevation estimations, there is actually a lot of information. It just looks for us noisy, but there is a lot of information that we can use, and which is reasonable. So we can also visualize a different way. So this is a kind of engineering way of visualization, just azimuth values and elevation values. But of course, we can do so that if we take the azimuth values and then the pressure signal and then kind of compute the cumulative energy, we can make these kind of plots in 2D. So what we have done here is that we have cut the impulse response. This is like the full impulse response is there on dark blue, and then we start from 5 milliseconds after the direct sound, and then again the rest of this, and then taking into account where the sound is coming from, plot this light blue, and then of course the dark blue is behind that one, so you are overlapping, but you can see that the difference between those is everything which is coming between 0 and 5 milliseconds. Then the green one is 50 milliseconds, and then the yellow one is 200 milliseconds. So in this case, you see that the direct sound is coming there, as we can see here. You have the reflection from the side wall, which is here, and then you have the reflection that we were looking for earlier from this back wall here. And then you have some other reflections. And if I do the same thing, that I close these panels and I open these panels, you can see, if you watch this, you can see that how the sound energy disappears from this side, and this one reflection disappears. We are not touching these at all, basically, but if I go back and forth, you can see how the sound energy in space actually is a little bit shifted. That's also shifted because now we have absorption on this side, So there's a little bit more absorption on that side than that side. And then when we move the absorption here, then kind of the whole sound field is in a way shifted a little bit. It's kind of the rare field is shifted, but the main information here is that how the reflections change, because these are really the strong reflections that we can see. Okay, if you do the same thing in concert hall, and now this is kind of the average of all these loudspeakers. As you can see, there are the direct sounds. And this is now the other way around, the time information. So basically the first gray here is only the 5 milliseconds. Then the black one is 30 milliseconds, the first 30 milliseconds. And then you see that you have the direct sound, and then you have also the bunch of reflections coming from the side wall from all these loudspeakers. And then also on this side, you get these reflections there. And then the last one is 200 milliseconds. So every single line here is 10 milliseconds more cumulative energy. And this way you can see that how the sound energy is distributed in space, in time. So where the sound is coming from. For example, here we see this kind of gap between the lines, which means that there's coming a bunch of energy here. So it's probably, how I could estimate this, is probably some because it's coming quite early. I'm not sure that where it's coming from, but definitely this is like coming from the back wall, this bunch of energy. And then the red line is kind of the full impulse response, kind of in space. So how it's spatially distributed, the full impulse response. And when this is really round like this, then we have learned that it means good envelopment. So then when you listen these, and then when you learn to read these pictures, then you can actually find out that how they sound as well. And these are all kind of relative to kind of the G values in room acoustics, so that you can compare different things, so different halls. Then of course you can visualize that in section, so you can see again the direct sound and then the floor reflection from there. You can see the under balcony reflections, which are coming here. They are quite early. Then a little bit late, you see the ceiling reflection. So the sound is going from the loudspeakers to the ceiling, and then again, and coming from between 30 and 50 milliseconds. And again, if you know how our spatial hearing works, then you can kind of understand that is this too early, too late, based on how our spatial hearing works. And then the back wall you can see nicely here, and then also the second order reflection, possible second order reflection from the back wall, and so on. And then you can see also the kind of so we have the plan. This is the plan, then we have the section, and then this is the transverse plane. So now we are looking to the stage, and you can see the side reflections from the lateral walls. You can see the under balcony reflections, and then the ceiling as well. And here you can actually see nicely also that our microphone has been tilted a little bit, because this is not exactly on the under balcony, and this is not exactly on the side, and this is also tilted a little bit. But luckily we can also kind of afterwards compensate this, so you can actually shift this to be properly oriented if you want. Okay, so this was kind of the visualization of the spatial information. Then how to do the oralization. The main benefit maybe in this SDM is that even though we are using these multiple microphones, the multiple microphones is used only for spatial information. And then we take one of these microphones. In theory, it should be in the middle of the microphone array, but it can be also one of these 6 microphones that we usually use the top microphone. And then we use the pressure signal from that one. And all of you who are dealing with audio or recordings, you know that if you have really high quality Omni microphone, which has flat frequency response, that always sounds good. Omni microphones, really high quality Omni microphone always sound good. So we are taking only one impulse response from this one Omni microphone. And this is the biggest difference, for example, for all ambisonics related techniques where you use multiple microphones and then you have to do the combinations of the microphones, and that's why you might get some frequency problems and then also kind of the directivity problems. But here we have high quality Omni, which is really Omni to all directions, and then really nice pressure signal, high signal to noise ratio. And how we do then the oralization is that now we decompose. That's where the kind of the name of the method come. Decompose this one omnidirectional impulse response. We decompose that on the loudspeakers that we have available. So in this case now, this is the listener, is the orange dot here, and then we have six loudspeakers in our reproduction. So this is a 2D case with 6 loudspeakers. So this is 30 degree. So this is kind of the left, center, right, and then surround channels. And then based on this analysis, we pick from this one impulse response, we pick all these samples which are coming on these angles. So in this measurement case, it corresponds everything, all the sound which is coming from here. So of course there is no direct sound because the direct sound is not coming from that direction, but you have this one bunch of reflections which are coming from the side wall. And then we put them all in this loudspeaker. So you basically you have a sparse impulse response in this loudspeaker. Then you take the next loudspeaker and you check the metadata. Okay, all these azimuth angles which are between plus minus 15 degrees, you take those samples and you put them in this loudspeaker or in this signal. And again, you have the direct sound, but of course you don't have the side reflections here because it's basically corresponding to this angle. And then the next one, the right channel, you have the other kind of reflections what you have there. And then from the side, we saw this small bump here. That was this reflection, which is actually coming from here. So maybe it's the balcony front or something like this, or it's the back corner of the hall. And then everything which is coming behind, you can actually see a small here, which is actually coming from the chairs behind the microphone. And then finally you have this one. So we kind of decompose this one omnidirectional pressure impulse response to 6 impulse responses. If you have more loudspeakers, then you decompose them to different directions. If you have a 3D case, then you decompose that to multiple loudspeakers. So in a way, you can see it also, as I said, that it's kind of the image. Every single sample is kind of representing an image source there. So basically, you have this kind of situation. Now we have these loudspeakers there, and then when we do this decomposition, basically you just do all these samples that you have in this direction. You just collapse to one loudspeaker, and this is your impulse responses on these loudspeakers. One more view is that you can also look at the signals now when we have decomposed it. So this is really the beginning of the signal in some small room. This is the direct sound, and then you have the floor reflection, and then you have the ceiling reflection and side wall reflection. And you can see that they go to different channels in this reproduction. And then what you do is then of course, when you have these signals, then you take your signal, which is hopefully anechoic signal, and then you do the convolution with all these sparse responses, and that's your oralization. And then you can repeat that for every single loudspeaker. For example, in this concert hall case, what we have been doing is that we have violins here, we have woodwinds in separate channels, and then we just take each woodwind and then put them in one channel, and then we repeat this for all different instruments. And then you can listen it here in the lab, like with the spatial reproduction technique. You can also do it, you can convert that to headphones, because when you know all these impulse responses for every single loudspeaker, which now picks from this one omni impulse response, you pick those samples which are coming from that side. And then if you want to do the binaural version, you just use HRTS from this direction and then convolve those with or it's kind of HRTS or head-related impulse responses, of course, in the time domain. And you just convolve these, and then you get binaural sound. Yeah, there's also, of course, when you do the binaural reproduction, then typically what we do is that we have this loudspeaker array, and then we use HRTFs as such. But then in some cases, of course, the loudspeakers are probably not in the really optimal place. So for example, if there's a really strong reflection coming between the loudspeakers, it's actually in this method, it goes to one of these loudspeakers, which is close by, but it's not exactly on the right direction. That's why it's really important that for the direct sound, like here, for the direct sound, you have actually the correct angle, one loudspeaker there, because that's what we hear. But then for the reflections, our spatial resolution is not so good that we cannot hear them exactly. It doesn't matter if it's come from 30 degrees or 35 degrees or 40 degrees, because it's a reflection, and then it's enough that it comes around there. So we don't need to be accurate, and that's why we can do this kind of, let's say, discretization to the channels. But if you want to do it optimally in headphone reproduction, you can optimize it for binaural rendering so that you look at the data that we had earlier with different visualization. You look at your impulse responses, where is the most energy coming from, and then you put your virtual loudspeakers with which you use the HRTFs, you put them in these spots where you have the biggest energy coming from. And this way optimize the loudspeaker, because in of course, when you do binaural signals, you can use whatever virtual loudspeakers. You are not restricted to physical loudspeakers, which you have to mount somewhere. But the loudspeakers can be anywhere. They can be also really close to each other if needed. And this is one paper that we did when you optimize, and you can actually reduce the number of loudspeakers. We found out that about 15 loudspeakers is enough to do kind of really convincing oralization of spatial sound. Okay, of course it's not the perfect technique. There are some limitations. There are nowadays workarounds for this, or compensations. You can read this paper if you are interested in about the compensations and the post-processing. But one thing is that with really transient signals, you can have this what we call roughness, because if you have a lot of loudspeakers, then your impulse responses from single loudspeaker becomes quite sparse. So there is kind of couple of samples, then there is zeros, then there's a couple of samples and zeros, and that means that you can actually hear this kind of roughness a little bit. If you have a transient signal, it smears out. If you have continuous signals like music or something, then you don't hear it. But with some technical signals, you can actually hear it. The other thing is that it's actually whitening the tail. It's the same reason, because you have a couple of samples, then you have zeros, and then you have again a couple of samples and zeros, and then you know that this kind of signal, the frequency response is almost white. So it's almost flat. So it's kind of whitening the tail, but again, you can compensate that as well. So there are compensation methods for these. these small things. But these are actually small details that you might deal with if you want. But it's working also just out of the box as such. And there is in MATLAB package, and there's also a Python package nowadays that is implementing this method if you want to try it. So the complete system is that you have these measurements with open microphone array. You measure the spatial impulse response. You take one of these microphones as mono impulse response. Then you do the direction of arrival estimation for every single sample, and then you use this one omnidirectional response, and then you kind of you can do the visualization, or you can do the oralization with some post equalization if you want, and then reproduction. Okay, in the end, I show you some applications where we have applied it, and then where others have applied it as well. So where we started it was concert halls, and we have done a lot of concert hall studies based on this oralization technique. So we have measured different concert halls, these spatial room impulse responses, what we called with loudspeaker orchestra, which you can see here. So there are a bunch of, we kind of simulate the orchestra with bunch of loudspeakers. And we measure from every single loudspeaker the spatial room impulse response to different seats. And then we can do the processing, and then we have anechoic classical music what we have recorded one by one in our anechoic room, the players, and then we can put them in different loudspeakers, different instruments, and then you can recreate kind of the spatial sound what is in the concert hall in the lab. And the benefit of doing this is that you can really do A/B comparison of different concert halls. For example, in these two halls in Berlin, you can put the symphony going on, and then you can jump between the halls and do A/B comparison, and you can really hear the details, really detailed small differences. So for example, here the visualization, we see already, this is kind of the shoebox hall, what we call shoebox hall, so rectangular hall, where you can see the direct sounds, you can see the nice reflections from the side, and then you have really round kind of spatial energy distribution in the end. So the sound is coming from all directions in the end, and that means typically good envelopment. Instead of this Berlin Philharmonie, which is this kind of vineyard hall, you see the direct sounds, but there are hardly any lateral reflections from the side because this is really oval. There is not this kind of bunch of energy what you see in the other hall here, and then it's actually more monophonic sound. And then also the kind of the late reverberation is not so round. It's quite round, but then there are some really strong reflections quite late, which you can hear as echoes, or it's also not so enveloping as such. In some cases, also the late reverberation is also really oval, and that means that there is not nice envelopment in these halls. You can use it also for smaller rooms. These are actually the studies that Neo Kaplanis did when he was working at Bang & Olufsen. So what he did is he was studying basically loudspeakers of Bang & Olufsen, and then took one stereo pair and then did the spatial room impulse measurements in different rooms. So he put them and the same loudspeakers and went to different rooms. Here you can see room A, B, C, and D, and then put them exactly on the same positions, and then you can do really A/B comparison of how these loudspeakers sound in different rooms. So this is not possible in physical space because you cannot, or you can go to a room and another, but you don't have exactly the same loudspeakers. Okay, you can have the same loudspeaker models, they probably sound the same, but you cannot do A/B comparison because you have to go from room to another. Another option is also that you can actually compare different loudspeaker models so that they are exactly in the same position. I think all of you has been listening to hi-fi systems side by side, but then the loudspeakers are always side by side as well. So they are not exactly in the same position in the room, and they excite the room differently. And then also we did some car cabins. So the car audio system, if you measure from every single element that you have in your car hi-fi system, then you can have this from the driver's head position, you can have your microphone array, and you can do the same process for these, and then listen those with a bunch of loudspeakers in an anechoic room, and then you can compare different car cabins as well, or different processing techniques there for the compensation of or equalization basically. We have also studied studio control rooms, so really dry spaces, and this was also a nice study that what we did. So in this case, there's 5.1 system in this studio, but then only 2 loudspeakers. So this is a stereo reproduction, and from this picture you can see that okay, there is the direct sound and then some other sound, but from this section picture you can see nicely that you can see the reflection from the floor, and also in this studio there was this kind of tilted ceiling, so there was really strong reflection. And based actually on this measurement, then now the ceiling is damped, so there is absorption, so that you don't have this ceiling reflection, because we all understand that it creates a comp filter and then you hear it. And in this study, which is actually reported 10 years ago in Journal of AES, we compared 9 different studio control rooms, and then we invited sound engineers who are working in these rooms to our lab to listen them, and they listened them blindly, and then we also did some A/B comparison and so on. And it was quite interesting that they actually blindly find out, just by listening, they found out their own room out of 9 different rooms, which was quite convincing to us that, okay, this method is really replicating the real environment quite well, because they kind of find out their own room. Of course, they are professionals, they have been working there like 10, 15 years, and that's why they know the rooms pretty well, but still they heard it, even though they were really dry rooms, and the reproduction system is in anechoic chamber, so it's really dry environments. Another, what we found out in this study was also that the mixing engineers, they prefer really dry rooms, not anechoic rooms, but they want to have really dry and neutral rooms. But then there were also some sound engineers who are doing mastering, and they actually preferred a little bit more lively rooms, because when they are doing their mastering job, they actually kind of typically probably their rooms are a little bit more reverberant and a little bit more live, and that was their preference. So we found out this kind of preference difference between kind of mixing engineers and then mastering engineers. Then we have studied movie theaters. These are just the visualization. I don't have the pictures of movie theaters, but these are the spatial sound systems. So this is the front, for example. This is the 5. There's 5. This is actually small mixing rooms where they are mixing movies, and these are really the cinemas where you have kind of left, center, right, and then you have some surround channels, depending on the theater how many surround channels you have. But based on these information, you can analyze these. But again, we did some listening tests, and then try to understand that what is kind of the difference between the small rooms where the movies are mixed, and when the soundtracks are kind of done, and then how they sound in a real cinemas. If you have a big cinema, you have a small room where when you do the sound engineering, but then you listen it in the big cinema, and what is kind of the translation in between those. Janne Rionheimo, who did this, he's defending his PhD later this year on this kind of movie theater sound, and especially the translation between the kind of the differences between the kind of the small mixing spaces, and then the bigger cinemas. And this is the last kind of fun example, which was on the COVID time, what I did. Unfortunately, now that the sound is not working, I cannot play this, but I can just explain what I did, is that you remember all that when the COVID started, then all the symphony orchestras, they couldn't play it, so they did this kind of YouTube videos where they all play at home their own part, and then they did this kind of collections. And they were really typically quite dry because they were at home and playing in their living room or something. They saw the conductor from the video and then they played their own part. And then what I did is that this is one symphony orchestra in Finland, and then I had their home hall measured with our loudspeaker orchestra. So I took these quite anechoic signals that they have all recorded at their home, and then used these spatial room impulse responses, and then I convolved with these, and then in a way I translated this kind of home orchestra to their own concert hall, and then sent back that, and they could listen the result, kind of how it would sound in their own concert hall. And this was actually quite popular at that time. It was done for headphones. Okay, to conclude, basically the spatial aspects of room acoustics can be measured with microphone arrays. There are many techniques. I now concentrated on this one spatial decomposition method, but there are also other techniques, and you can do this kind of visualizations, a little bit different visualization with different techniques, and then you can extract a lot of information, and especially in oralization, it helps a lot when you have the spatial aspects as well. So this SDM, it's based on time difference of arrivals of open microphone array, microphone pairs, and in rendering, the benefit is that you can use one monomic response and then use this metadata to basically use whatever reproduction loudspeaker method whatever reproduction loudspeaker array that you have. You can have 5.1, you can have 12 loudspeakers, you can have 50 loudspeakers whatsoever. And it's actually used nowadays, this method is used in Bang & Olufsen, and Meta Reality Labs is doing work also based on this method nowadays. And there is a free toolbox. If you just Google SDM toolbox MATLAB, then you can find it. Okay, that's it. I think we have spent 1 hour. Thanks for your attention, and I hope that also the Spanish-speaking community got the translation well. I think we can go to the questions.
Thank you so much. That was a very interesting topic, and we keep digging into impulse responses and decays, and understanding that it's not just about a slope, right? There's a lot of information there. So please use the Q&A for adding questions, and we still have a few minutes that we can answer a couple of questions, see if there are any. You can also add any messages to the chat, but please use the Q&A for questions. I don't see any yet. I think everything was very clear.
Okay, there's coming.
I'll give you a minute so you can type your questions. No worries. So in the chat, Gustavo is asking if you have measured the sides and the back of the Berlin Philharmonic.
Yes, we have about 15 positions all around, kind of also behind the orchestra and on the side of the orchestra, and they actually look quite crazy. They don't look so nice round, so they are really kind of not the hedgehog, but really different way, and they also sound quite different. So this is really showing this kind of surround halls that they sound different. Of course, our loudspeakers are probably more directive than real instruments to some extent, at least, and that makes also a little bit different, all kind of the difference as well.
So we now have a question. It says, great presentation. I work in virtual acoustics in recording studios. And my question is if you have done any perceptual study to compare the sound quality of spatial room impulse responses captured with the SDM method with other methods like ambisonics.
Yeah, there are a couple of papers done by different people, and then it seems to be really signal dependent. So some of them found out that some other methods sound better, but then there was a recent study done in I think it was the University of Huddersfield, where they found out that the SDM was based on there was the best one. But if you send me an email, who was the asking person, so tapio.lokki@aalto.fi, which is kind of, you can see, I can send you the links if you just send me an email, and you can write in Spanish as well, and I will find out the information. And I can send you a couple of links to these papers. Good.
That's good. Another question, Dr. Lokki, thanks for the presentation. Do you think that there is necessary to develop objective parameter for very small rooms like control rooms? Because IRs are extremely short. Thank you.
Yes. Yeah, of course, IRs are not enough. What seems to be also really important there is the frequency response, which you can compute from the IRs. So basically, if you measure the spatial room impulse response, then you have all the information. But then, of course, you need to check kind of the frequency response. In some studios, people are really keen on that you don't have any reflections coming inside 15 milliseconds, so that you have enough time to hear your loudspeaker well before the room kicks in. So it's all these kind of things. Direct to reverb ratio is one thing, even though they are really dry rooms, but how much and when the sound is coming from. So I think there are some parameters, or there is not parameters, but there are things that you can actually find out, and there is information, and all this information basically is in there in the spatial room impulse response. Now everything that I showed was done wideband, but you can do it also in the frequency bands. And we have done it some. For example, when we did the movie theaters, we actually did the rendering in octave bands, because in movie theaters, the main channels are huge loudspeakers, and they're actually the high frequencies are coming from different spot than the low frequencies or the mid frequencies, because they are just big loudspeakers and the elements might be 1 meter apart. And then just to be accurate, you can do it also in bands. But of course, it's more processing.
Great. There's another question in the chat. Thank you very much, Tapio. It's a fascinating development. What do you think about evaluating ARs from the transition time? Greetings from Buenos Aires.
The transition time, do you mean what you mean transition time? It's probably the time when kind of the sound energy is balanced kind of before and after there's the same amount of energy, or the transition time could be also that when the kind of the reflections end and then kind of the late reverberation is taking over. And the question was, what do you think about evaluating? Yeah, my problem always with the transition time has been that it's not really well defined. There are many methods to kind of compute this transition time, but they all give you different answers. And for me, it's kind of, I don't trust the transition time at all. It's kind of, you can have reflections coming from, and then you hear them, they are widening the sound, or they are coloring a sound a little bit, but then when it starts to be a late reverberation, I don't know. But for example, in small rooms, it's kind of what I told about concert halls is kind of the air reflections and then envelopment, which is kind of the late sound. But in small room, everything is so short that it's kind of the width, kind of the wideness and envelopment is almost the same, and they seem to be kind of really close to each other. So, for example, this is something that it's kind of just widening the sound if you have strong reflections from the side.
Okay. There aren't any more questions at this point. I want to thank you again for this presentation. It's fantastic. We had a good group of people here. Please join the chapter if you're a Spanish-speaking acoustician anywhere in the world. We invite you to become a member. And if you just want to find out when we have more presentations, you can follow us on social media. We have at least 3 more presenters for the rest of this year. So we try to do about 1 topic per month. Follow us and find out what's next. Thank you again, Tapio, and thank you everyone for attending.
Okay, thanks a lot. Bye.